Number 59. So given the curves y equals x squared, revolved around the line y equals -1, we need to find the volume. So if we have a case like this, where you have two curves, and it's going to be a vertical rotation. So around a horizontal line is going to be a vertical rotation. You're going to use this formula. So it'd be pi times the integral from a to b, and the a to b will just be these two intersection points, of f of x minus the axis squared minus g of x minus the axis squared dx. So we just have to find out what these things are. So from a to b, we just have to find out when y equals x and y equals x squared will intersect. So to do that, we just solve the equation x is equal to x squared. And you don't even really have to solve this one. You can kind of just think this is going to happen whenever x equals 0 and x equals 1. So we're going to have bounds from 0 to 1. And then f of x is going to be your upper function. So during this interval, your upper function is going to be y equals x. So f of x is going to be x minus your axis, and our axis is -1. So it'll be minus -1, or x plus 1. So, and then that's squared, minus g of x, which would be x squared, plus 1 squared dx. So let's go to the calculator, and we can just calculate this real quick. So it'll be pi, and then to do an integral, you can do menu for 3. And then we're evaluating from 0 to 1 of x plus 1 squared minus x squared plus 1 squared, and then dx. So we get a volume of 1.47. This is going to be 1.47. All right, let's go to number 60. So number 60 is pretty tricky, but there's usually more than one way to do this. But I'm just going to show you the way that I found that I think is the easiest way, even though it's still a little bit long. So let's see, we have a semicircle, and then a rectangle, and an isosceles triangle. So semicircle, rectangle, isosceles triangle. We're told that theta is greater than 2 radians, and the hatched area over the semicircle area is 0.78. So I'm going to change this a little bit, or not really change it, but simplify it. I'm just going to make the semicircle area equal to 1, and that way we'll just know that the hatched area is 0.78. So if the semicircle area is 1, so if this part right here is equal to 1, then we can find the radius pretty easily. We just know that 1/2 pi r squared is equal to 1, and we can solve this real quick. So it'll be 2 divided by pi, and then the square root of that. So we'll get an r, or a radius, of 0.79788. So we're going to use this throughout the rest. So I'm going to just call it r, and then in the end, I'm going to plug in that value for r. So what we have to realize here is that these white portions, the portions that we're not finding the area of, these white portions are really just segments of a circle. So for example, this area right here, if this is the center of our circle, then we draw these these segments, and you can see this is part of the segment of the circle. This is the segment of the circle. So to find that area, we use the formula. Let me erase a little bit. The area of a segment is 1/2 r squared times the central angle, so this angle. So 1/2 r squared times theta minus sine of theta. And we're just going to have to find some values of theta. So let's see. This total angle right here is theta. And so that means this right here is going to be theta divided by 2. Then if that's theta divided by 2, then we also know that this right here is theta divided by 2 because the side lengths opposite them are equal. So the side length opposite this theta over 2, side length opposite this angle is going to be a radius, and the side length opposite this angle is also a radius. And so we know they must be the same length and therefore the same value. So then for this final angle, this angle that we actually need for our area formula, you think about there's 180 degrees in a triangle, which corresponds to pi radians in a triangle. So if I call this angle alpha, that means theta over 2 plus theta over 2 plus alpha is equal to pi radians. So alpha is equal to just pi minus theta. So this angle right here is just pi minus theta. So we can find the area of that segment then in terms of theta. So the area of that segment will be 1/2 r squared. And I'm just going to keep writing r, and then I'll substitute in our longer value, our 0.79788, at the end. So we have 1/2 r squared, and then the value of our central angle is going to be pi minus theta, and then minus the sine of pi minus theta. So that gives us this area right here. And if you notice, that's actually going to be the same area as this over here. So in total, we're actually just going to have r squared times pi minus theta minus sine of pi minus theta. So we have these ones taken care of. These ones are taken care of. Now we just have to look at these ones on the side. So let me get rid of that. I'm going to keep this as pi minus theta. And so these other ones are also segments of a circle. It's just cut in half. So imagine that this part over here is sort of brought into this area. Or in other words, these are just both half of a segment. So we have the same radius. So I'll call this area of segment 2. It's still going to be 1/2 r squared. In fact, it's only going to be 1/2 r squared. There will be no doubling because each of these is only 1/2 of a segment. So it will be 1/2 r squared. And then as far as the angle goes, we see that these two angles, so this angle right here that we used in the previous segment, that angle and this angle are going to be complementary, where they're going to add up to be pi over 2 radians. So if I say pi minus theta, and then I'll call this angle alpha again. I know I've already used alpha, but I've erased since then. I'll call that angle alpha 2. So pi minus theta plus alpha is going to be equal to pi over 2, since this right here is a right angle. So then if I solve that, I'll get alpha is equal to theta minus pi over 2. But that's not actually the angle we're going to be using, because that's only half of our segment. So we actually have to use this angle right here. And that's just going to be twice that. So really what we're going to be using is 2 theta minus pi. So for the other part that we're going to have to subtract, the other white area, we're using the angle measure of 2 theta minus pi. So it will be 2 theta minus pi minus the sine of 2 theta minus pi. All right, so now what we know the areas of these ones. Those together will be r squared times, or this part right here. And then the areas of these two portions together is equal to this right here. And so if we add these up, we get the total area of the white space. And then we can find the area of the hatched area by doing just 1 minus that, because we said the area of the semicircle was 1. So then if we set that equal to 0.78, solve for theta, we should get the right answer. So this is a pretty complicated equation. So I'm actually going to go to my calculator, and we're going to use a solver. So first of all, let's find the radius. That was going to be 2 divided by pi, and then the square root of that. So the square root of that. And I'm going to store that value as r. That way we make sure we have an exact value of r. So now I'm going to set up our solver now. So the first part is, we have to make sure we're subtracting from 1. So the first thing we do is 1 minus, and then So it's going to be 1 minus the white area. So the first part will be r squared times pi minus theta minus sine of pi minus theta. So r squared times pi minus theta. So I'm just going to use x because I don't want to have to go back and use theta a bunch of times. So r squared times pi minus x minus the sine of pi minus x. That's the first part. And then we have to add to that the other parts of the segments, the other segments. And that's 1/2 r squared times 2 theta minus pi minus sine of 2 theta minus pi. So 1/2 r squared times 2 pi minus x. It is 2 pi minus x, right? Sorry, 2x minus theta. Sorry, 2x minus pi. I messed it up. 2x minus pi minus the sine of 2x minus pi. And altogether, we found out that this, according to the little bit we have at the bottom, the hatched area will be equal to 0.78. So equal to 0.78, comma x. And at the end here, I'm going to make the stipulation that x is going to have to be in between 2 and 2 pi. Or not 2 and 2 pi, 2 and pi. And the reason I'm doing this is because it tells us that the angle is greater than 2, and we can tell just by looking at it that it's going to be less than pi, or less than a straight line. So if I do this, click Control Enter, we should get the angle measure. So if I do Control Enter, we get an angle measure of 2.33 radians. Get an angle measure of 2.33 radians. So that's a pretty long problem, and like I said before, there's usually more than one way to do these problems. And so if anyone has an easier way, I would be more than willing to hear it because, like I said, this problem is pretty long. But anyway, if you have any questions from other tests, make sure to leave a comment and I'll make a video with a solution. With that said, if you enjoyed the video, leave a like and subscribe. This has been Investigative Math, and I will see you next time.